I got a soundbar for my laptop, and it was a very simple setup. My laptop had a simple mini headphone socket, which is a TRRS, tip, ring, ring, and sleeve. So that allows both your headphone out and a mic in using just one plug if you wanted to use it. And the soundbar had two simple mini headphone plugs, 3.5 mm as well, and each of them was TRS, tip, ring, and sleeve. One plug was for audio out, and the other one was for mic in, and it was powered by a USB port. So it looks like any generic sound bar that you can get, and I got this from a popular online retailer. And it was working fine overall. It did the job for my limited needs, but there were two annoyances. One was that it was left and right swapped. So somebody had swapped the left and the right channels from the input of the TRS plug going into the soundbar and the amplifier. Somebody had swapped the left and right during manufacture and nobody noticed it. But that was fine. It was okay with music. It was okay with little bits of audio material that I was listening to. And it had a narrow sound stage anyway, and you could hardly tell it was stereo. I don't watch movies on this, so it wasn't a big deal of having to have the audio coming out on the correct side of the viewing area. The other annoyance that I had was this pop that I noticed that happened just before and a few seconds after the audio material was played. So this was not all the time, but it was fairly regular, and something was going on there, and after a while it started getting a bit annoying. So was it a noise gate? A noise gate is a technique to handle background noise or hiss, often used in cheaper circuits to hide the noise during sections of silence in the audio playback. Basically what happens is that you have, if you had noise in the background, either because of cheap circuit design or the environment was inherently noisy and you couldn't get rid of it, then if you imagine, instead of a nice quiet audio background when there was silence, you would have just this background noise happening all the time. And this usually makes itself apparent by a hiss in the background. And what you would do then with the noise gate is that, well, if you had, let's say, your normal audio material that was going on here, and when your audio material stopped and it was silent and you had the noise coming through, then you would have a control or a detector which would detect that there was actual audio material, and when the audio material stopped, it would shut off the output. So the effect then is that you would have your audio material here, and then after that, your output would be a nice, quiet silence. But that was only because you had actually shut off the connection to the speaker or the audio completely. So was it that? Or was it from the laptop? Was the clicks or the pop coming from the laptop? Now, the thing was, it was not noticeable coming from the laptop speakers and not noticeable through earbuds plugged into that TRRS socket. So that was interesting as well. Or was it maybe then from the soundbar? And in order to have a better idea of what's going on, I would have to open up the soundbar to see the amplifier chip and to get a better sense of how it was wired up. Now, here is a look at the connections to the audio module of the soundbar, and you can just about see that these sockets are connected or mounted on the PCB, which is just on this side of it. So when we look at it with the PCB below, what we notice is that we've got red, which presumably is the right channel, on the left of it, and you've got the white, which then would be the left channel on the right of it. When I removed the PCB just to have a look, and now we're looking top down again as well, lo and behold, what do we see? On the left hand side it is the left, and on the right hand side it is the right, which is the opposite of how it was shown in this way. So somebody had just plugged in the wrong plugs into the sockets, and that's why I had a swapped left and right. But that was a minor point. And just to clarify, this is the speaker out. So the input comes from this side, and this is where it gets its input signal through the TRRS mini headphone plug from the laptop. It also puts out the microphone, the mic input. So there's actually a microphone in this soundbar. It gets amplified by this amplifier chip, and it drives the speakers through these two sockets. So we've got left and right there. Looking at the amplifier chip, I realized that it was one that was very similar to a US company, which is this one, which is by Diodes Incorporated, the PAM8403, and it's a Class D audio amplifier. And it was something that's to be expected because you've got high efficiency with the Class D, and you don't want to be drawing a lot of current through the USB port if you didn't have to, especially if it's powered from a laptop. This is the actual chip, which has almost exactly the same pinout, and it's made by the company Mix Inno, and the only data sheet I could get was in Chinese. And that's fine. What we need really to see is how the connections go. And what we see here is that the inputs are connected to the actual chip using some DC blocking capacitors. Now, of course, this is to be expected again because the chip is supplied from a single-sided or single-ended power supply, if you like. It's only from a positive and ground, and there's no negative. So this whole chip works within the DC level, and it needs to have a blocking capacitor put in here. On the laptop side, the sound chip is, according to the information from the laptop manufacturers, it's the Realtek ALC250, which is really, really common. And the way that it's connected is here. Now we've got a choice of either the auxiliary or the headphone out signal to drive the audio out. No way of actually seeing which one they've used without opening my laptop, and I wasn't going to do that. But electrically, it looks very similar. You've got 100 microfarad capacitor for each of the auxiliary lines, or the same thing, 100 microfarad capacitors for the headphones. The only difference, though, is that the auxiliary lines can be programmed to be both inputs and outputs. Since the audio out jack through the mini headphone is a TRRS, then it's quite likely that the configuration will be one of these, and actually possibly this one. So you've got the auxiliary, and it could be the headphone as well, given how it's working, and we can't quite tell. So we've got, at least for the purposes of what I'm using here, I've got the audio out, and it goes through the TRRS socket, and we also have an internal mic in. So this would be the microphone at the top of the laptop screen, which should go in, and between the chip itself and the output, as you can see, there is you've got the sets of DC blocking capacitors. So it goes through a DC blocking capacitor, through here, through some ferrite beads and some small capacitors just to keep out any EMI, and you get the output through here. At the same time, you have Vref, a DC voltage, which is 3.3 or 4 volts, 2.5 or 4 volts, going through a simple diode. And you have a detection which can tell whether you've got something plugged into the socket. The full connection between the laptop and the soundbar, and we're using the recommended or the suggested, I suppose, circuits on the data sheets. There's no telling if this is exactly how it's done on the circuit board, but this is the best guess we can do, at least on the laptop side. And even on the soundbar, although I opened it up and we can see the circuit board, I haven't done the trace, so we can't say for sure if they followed things exactly the same. But let's see, we'll do the best we can with what we have. So we've got these connections out here. So it's either using the headphones out or the aux out. Connections are basically the same. So we will, doesn't really matter which one we use, at least for our rough guess here. And we've got the LC250 on the laptop. And we have the outputs there with the DC blocking capacitor. Make that a bit longer. And now this goes to the socket. Well, on this one, it's got the DC blocking capacitor, and then it continues to the socket following this. So again, there's no telling if they've actually used the same method as what they've shown here on the laptop circuit, but we'll go with what we have here. Now, just to follow the convention here, we've got the right channel there and the left channel there. After going through the DC blocking capacitor, it goes straight to the socket. Now we've got two ferrite beads there that they've put there, including two small capacitors, and this is just for EMI, electromagnetic interference filtering, so that all the noise from this side does not go through out into the outside world. But functionally, it has no effect on the audio functions, so we'll leave that out, and we'll say it goes to the socket here. There is now, as well, this Vref out with the diode to the aux L, or to the left channel, and the Vref out is, so I think it's something like 2.5 volts or 4 volts or something like that, but it's a DC voltage, and through a simple diode to the left channel on the outside of the DC blocking capacitor. And on the right channel, we've got 22 kilo ohm resistor down, which I don't think does all that much when we've got something plugged into the socket. So if we have a closer look, on this side, we have the DC, we've got the 22 kilo ohm, but that goes through up here 10 kilo ohms into JD2, which is the jack detect pin. And this, according to the data sheet, is pulled up by, I think it's 50K. So this sets up a little bit of a potential divider all the way from there. I'm not sure what it is, I think probably up to 5 volts. And based on what voltage is here, the sound chip can detect whether something has been plugged into here, or when you plug it in, then these terminals 1 and 2 open up and the voltage changes. Now, once we plug it in, it goes to the amplifier on the soundbar. So we'll just draw this here. Again, amplifier on the soundbar. We've got another set of DC blocking capacitors, a resistor into the soundbar itself. And that's quite simple. So this is the 31.8, and this now goes out amplified to the speaker. Next, I decided to have a look at the socket of the laptop here, or if you like, it was here. I unplugged the soundbar, so there was no load and it was just open. And I plugged in an empty plug so that I could get connections to the left and the right and the ground. And I decided to see what was being presented there. I was thinking maybe there was something to do with the low power mode, or as I was saying earlier, a sound gate, but I think it turned out to be a little bit more likely that it was some kind of low power mode setting that was causing the clicks or the pops. Let's have a look. Now it looks like when it is in the soft low power mode, interestingly, the left channel, which is the green trace here, is at about 770 millivolts DC, or it exhibits a 770 millivolt DC level, whereas for the red trace, which is the right channel, it shows about 5 millivolts. So there is a DC level when nothing is running, and when we play an audio file, which I'll play now, let's see what happens. Okay, first we'll change the trigger to normal, and we will wait for the trace to trigger and we can see what's going on. So I'm going to play an audio file, not a very, very short audio file, and let's see what happens to the DC level. Right, so now we can see that the right channel, which has a short blip there, goes down to a negative, and then it plays the DC, plays the audio, and it stays on at about 0.5 or 5 millivolts DC. Whereas for the left channel, it goes down from about 770 millivolts all the way down to 0, which is interesting to see. And now when I close out the app that plays the audio, 2, 3, 4, 5. So after 5 seconds, we see that the right channel has another click from just over minus 10 millivolts. And for the left channel, it goes back to the 770 millivolts. All these DC levels that we're seeing, the DC level, which was 770 millivolts, was on the left channel. And so this was really, it seems to me that it comes through the VREF out, through here, through the diode there. But it comes and goes depending on whether the audio is being played or not. So I'm not quite sure how that works, but it does seem that the 770 millivolts comes through here and is controlled and switched on and off by the sound chip. It occurred to me that with DC voltages going up and down and no corresponding clicks when I was listening to it through headphones or earbuds, that there may be something that's going on with the low impedance when it's plugged into the socket over here, or on this side if you like. So what I decided to do to have a look was to remove the connection to the soundbar. Let's see if this works. Almost does, except for that one. And just plug in headphones there. In other words, I would have fairly low impedance to ground through my headphones or my earbuds, possibly something like 32 ohms or so, 30 to 40 ohms. So we've got maybe 40 ohms here and another 40 ohms there. And maybe with resistors or a low impedance to ground, that would have some effect on the voltages and the clicks that we were seeing. To actually connect a low impedance or low resistance between this connection, this output and ground, and this to ground, I use a resistor, I think it was 39 ohms, 1x1, to see what effect it would have on the DC value. So let's see what the scope showed us when we tried that. Right, so let's see what happens when I place a resistor, a low impedance, across the left channel, and you will see. So I'm going to touch the resistor there, and now you will see that the left channel has gone down from 770 millivolts all the way down to 0. Now if I do that with the right channel, you get the contact there. Now we'll see that the right channel has gone down to 0 as well, but there's a lot more noise because of just the pickup from the cable. Now if I remove it, you will see it goes back up again to about 5 millivolts. At this point, I have connected a low impedance of about 47 ohms to the left channel, and what you see is that it has brought down the left channel all the way down to basically 0 volts DC. And I'm going to play the same short audio file now, and we'll see what happens. We'll change it to normal, and let's play the audio file. And you will see that like before, the right channel has that very short negative click or blip all the way down to about minus 10 millivolts. The right channel, on the other hand, is perfectly fine. It stays down at 0. There are no more clicks or changes in DC voltage level. It plays the audio and continues. Now let's watch to see what happens when I close out the audio app. 3, 4, there we go. About 5 seconds after that, the right channel again has that click or that dip down to just beyond minus 10 millivolts, and the left channel is completely fine. It just stays at 0 volts. Now I'm going to change the swap round the low impedance to the right channel. Now you can see that the right channel is a lot noisier because of the additional pickup from the cable. But let's see what happens when we play an audio file. So I'm going to trigger it on A. Just set it here, and you can see it's running now very nicely with the right channel more or less down to 0 volts, and the left channel, because it does not have the low impedance connected to it, it's back up to about 770 millivolts there. So let's set the trigger correctly, and I'm going to play the audio file again. And again, you see, just before playing the audio file, the left channel drops down from 770 millivolts down to 0. The right, interestingly, actually goes up by, it looks like about maybe 3 millivolts DC. It plays the audio here and then stays there at that level. Now I'm going to close out the app. 2, 3, 4, and about 5 seconds later, we can see the left channel going all the way up back to 770 millivolts. The right channel stays more or less at the maybe 3 millivolts, and then it goes back down to 0 volts there. So there are all kinds of things going on as the output, as the laptop is trying to play the audio. the low impedance to ground seemed to work, I decided to do that. In other words, I decided to put it here. Oops, let's draw that a bit more clearly. Okay, from here to ground, and from here also to ground. And this would be something low, but not too low, of the order of what you would find in headphones or earbuds. So what would work would probably be anything from about 40 to 100 ohms for both of them. And that should solve the problem. And so what I did was I rummaged around for two resistors that I had with the same value. Turned out to be 68 ohms. So that would be fine, I thought. I soldered it between the left and the ground and the right and the ground of the input to the soundbar. So it was around here. And once I did that and plugged it in, it solved the problem. No more clicks and pops. In the meantime, while it was open, I thought I'd have a look at what was coming from the Class D amplifier. And so this is what I saw. This is a typical Class D output, nice square wave with a 50% duty cycle, and this was with no audio material at all. And when I was playing audio material, we see a little bit of a heat map, if you like, and the falling edges would change in time based on what the sound material was. So this part would drift back and forth, or would move back and forth, whereas the rising edge would remain the same. From what I could see, there wasn't really a lot of filtering. Maybe they were depending on the kind of natural frequency response of the loudspeakers to filter it off. And they were basically pumping in this PWM straight into the loudspeaker. So as you can see, we have the PWM going at a frequency of, let's say we've got 1 microsecond. So this is 1.5, let's say. So this would be, if it's microseconds, so we've got megahertz, and this would be 500 kilohertz. So I make that maybe about 700 or so kilohertz, which is way above what any loudspeaker can handle. So using a PWM wave at about 700 kilohertz, naturally that would be filtered out, and what you would have in effect left behind is the sound energy within the hearing range.